We are studying IGCSE physics, and today's agenda is going to be all about learning nuclear physics 3, and in that we'll be learning about half-life questions, deflection of radioactive particles, and radioactive decay questions. So mostly questions and a few things which we may have left out or not properly studied. I start with half-life questions. Just a second. The rest of you tell me, check your book and tell me what have you studied in the last class for nuclear physics. Give me a recap. Check your notes. Quick.
Sir, we did revision, I think.
Revision of?
Chapter 3.
Now we did that. What about nuclear physics? Check the notes for nuclear physics. We looked at radioactive particles. We looked at what passes through, what is the penetration, everything. What else have we did? Neha, tell me, what did you do in the last physics class?
One second. We did those questions from like the past papers, I guess.
Past papers, I see. Half-life. Okay, let's see. Let's do this question. Let's start. Read the question.
Yeah. A radioactive nuclide has a half life of 4 days. A sample contains 9.6 into 10 to the power of 8 atoms of the nuclide. Calculate the number of atoms of the nuclide remaining after 12 days.
Okay, so what's happening here? The radioactive nuclide has half-life of 4 days. We'll write it down. Okay, now after that, we also realize the sample is equals to this much. Okay. Now, how do we find the number of atoms after 12 days? Now, we realize that after every half-life, the number of particles, let's say the sample halves. The sample and activity / activity halves. Same thing, sample and activity, they half. But now we have, instead of 4 days, we have 12 days. So let's see how many half-lives. How many half-lives are passing? To find that, we'll just divide 12 by 4. And how much do we get? Tell me. Well, by 4, that's 3, right? So 3 times, it must be half 3 times. So we'll multiply this sample with, let's say, sample left is going to be 9.6 into 10 raised to the power 8 into half into half into half. Now, any questions, ask me. There is a better method to do this, but I'm just trying to make things simple for you. Now, tell me, do you understand? Any questions?
No, sir.
Neha, tell me, I want you to read the question one more time and explain to me, how do we answer this question? Should I explain?
One sec.
Part A.
1 second. 6. 1 sec. Yeah. Okay. Calculate the number of atoms of the nuclide remaining after 12 days. So the molecule's half-life is 4 days, and
Okay.
above that it's given that a sample contains 9.6 into 10 to the power 8 atoms of the nuclide. So that's what the sample is. And then 1 sec. Okay, so you divide 12 by 4 days, and then 12 is basically the total number of days divided by the half-life. That's 4 days. And then after that, what's left is that 3 days. So no, 3 times. So you multiply it by 1 by 2, or like half, 3 times, and then you get your half-life.
Half-life. So what is the answer? Anas or Ayan, tell me.
Sir, it's 12 by 4.
12 by 4. Are you sure? What is the final answer? 9.6 into 10 raised to the power 8 times half, right? 3 times.
Oh, wait, 1 second.
Neha, tell me the answer. I can't hear you.
Can you hear me now?
Yes, tell me. So what is the answer for this question?
One
Multiply all
second.
of these together.
Yeah.
Is it 9.6 into 1 over 2, 2, 2, 4, 8, 8, 9 by 6, that would be 1.2, and 10 is by 8. Is that the answer?
Yeah.
Perfect. Okay. Now we're getting these. This is the answer. But I don't want you to do it in this way in the exam. There's a clear formula. So please
One
write these
second,
formulas
sir.
in your notebook. Yes. Tell me.
No. Nothing. Yeah.
Okay. Now write in the formulas. Formula for finding number of particles. Let's say number of particles or activity given half-life and time. Write the first part here and write the two formulas. 1, 2. Tell me when you're done writing.
It's half to the power t by t 1 by 2, or half into
No, it's
t.
half raised to power. So just a second. Let's make it more clear. Stop writing. Let's make it a little bit more clear. Now this is raised to power. So
Yeah.
A, original, let's say original number of particles multiplied with half raised to power t divided by t half. Okay.
So
Whatever
we
the
could
time
say
is.
raised to the power 2t by t.
Raised to power 2t by t. No, not really. No. This is not half. The t half over here is my half-life. Okay. I'll tell you all of this in a second. T half is half-life.
Okay.
N0 is, or N naught is original number of
Original.
particles. Original
Yeah.
sample. And N is sample left. Write all of this down. Now, one thing we need to realize is that this over here is raised to power. This is power. Okay. Any questions? Neha, any questions?
Not really.
I have a few questions, but I think they'll get solved once we try to solve the
Yeah.
question.
Question, right? So write this down quickly. Ayan, have you finished writing?
Almost, sir.
Okay. I'm done. I'm done.
You're done. You have to write this part as well.
They're done.
Yeah, I did. Okay.
Perfect. Okay.
Can we just substitute it into the formula in the next
Exactly.
question?
We'll do that. Let's try to solve this question again, but in a different way. Okay. We have done this one more to one. We have done it once. Let's try it one more time. Now in this question, they're telling us the half-life. Okay, half-life is given. The sample is given. So this will be our N0, the number of particles at the original. And this is my T half. And this is my time, T. So I know that N is N naught into half raised to power T divided by T half. Okay, so N naught is going to be 9.6 into 10 raised to power 8. All of this multiplied with half raised to power T, which is 12, divided by 4. Now give me the answer. It will be the same. And check if it is the same.
Wait, so T is time, right?
T is the time, yeah, so which will be given. T half is the half-life, the time for the half-life, right? And N naught is the original number of particles. N is the number of particles we're trying to find. That 0 basically means the original. We call it N naught. Any questions?
No, sir.
No, sir.
Now next question.
Another question.
Anas, read the question.
Sir, could we do another question with the formula?
The
Yeah, this
count,
one also has formula. Yeah, go on.
Okay.
the count rate from the sample is measured in a laboratory where the background count rate is 16 counts per minute. A detector is placed at a fixed distance from the sample. The initial count rate measured by the detector is 160 counts per minute. Calculate the count rate measured by the detector after 12 days.
After 12 days. Okay. What's happening? Let's again identify our key variables. After 12 days, that's my time. That's how much I have to find. This is my count rate or activity, right? So at the initial count rate basically means activity. There are two equations here which are basically the same thing, same as the first one, because number of particles and count rate are proportional. This is my original activity, and this is the background. That's the background radiation. Okay, now what are they asking us? They're asking us to find the count rate after 12 days, right? Now, one thing we need to realize is to find the count rate because of the particle. Let's make a diagram here. Perhaps you have a particle here, which is radioactive. Okay, this is, let's say, uranium, very radioactive. And I have a count rate measure thing here, which is measuring the count rate. And it's connected to some device, which some meter here, which gives me a reading. And it's saying, let's say, at the beginning, it was telling me that the count rate is 160. Now you need to realize that not only the particles are coming from here like this, let's say particles are coming like this to it, but you need to realize that particles other places or around the uranium are also giving some radioactivity. Now this right here is the radioactive particles, or let's say radioactive particle, right? And they're hitting this count rate thing, the count meter, as we call it, count meter, and it's giving me some reading. But the uranium is not the only thing giving us, the uranium sample is not the only thing which is giving us the reading. There are more things around the uranium. Let's say some rock, or let's say there's some rock here, and all of these things, or perhaps there's some other kind of thing on a table here, some other substance, we don't know what, which is also giving us some reading. So these guys are giving not so much, very small amounts of reading here, very small, very small. So we realize that this right here, or let's give it even a smaller thickness, it's very tiny, about this much, is also coming towards the count meter. This right here is called the background radiation, which is not because of the sample, but other things in the surrounding. Background radiation. Okay, now Neha, any questions? Ayan, Shrey, Anas.
No questions.
No.
Now, what is Neha? What is the background radiation? Tell me. Neha, I can't hear you. Shrey, what is the background radiation? Neha, what is the background radiation?
The background radiation is basically the radiation that's already present in the background before the sample was put in there.
Exactly, because of the surrounding.
So that's
Now,
radiation
what's-
from the environment, right?
It's from the environment, right? From the surrounding the environment, right? Now, same thing. So what's happening is it is not from the sample, it's from somewhere else, from the surrounding or from the environment. Fine. So therefore, the count rate here is not accurate. Why is it not accurate? Because it's not only from the sample, we also have some interference, some additional uh,
Yeah.
let's say radioactive particles coming.
Purely from the sample, yeah.
Right. So now what we have to do is the count rate, the total count rate is because of sample plus surrounding. And to find sample only, we'll have to subtract surrounding from the total count rate. Right? So total count rate minus background or surrounding. Fine. Now we know what the background radiation is. Instead of surrounding, I'm going to call it the background radiation. Now we already know in the question that the background radiation is how much? 16 counts per minute. Before we put the sample, it was already the background rate was already 16. Fine. So what we have to do is total count is 160. Surrounding was 16. Therefore, the sample is how much?
144.
144 is sample. Okay. Now this is the one which we're going to put in our equation. The sample activity, right? The sample activity is 144. So let's use the equation again. Let's write it down.
So
A
the
is equal
original
to A naught.
activity is
Yeah. Neha, tell me the equation.
okay, A is equal to A original
A naught into half
into half into T to the power T divided by T half.
T half. Now, Ayan, tell me the values for A naught, for A naught, for T, and T half.
Should I just tell you?
Not really, no. Anna, Shray, you can tell me in the chat. I need the
Sir,
rest of
T is
you
12
to.
days.
T is 12. Okay.
A was 160 counts per minute.
A was 100. No, we don't know this one, right?
No,
We don't know this.
AO.
AO is not 160. Why? Because 160 is the total because in the surrounding plus sample. We need only the sample.
Yeah.
Okay. Only the sample. So we'll put 144 here. We need the AO or the activity of the sample at the beginning, not the background radiation. We have to remove the background radiation and just put 144 divided by T half. They are
half
telling
is
us
6, right?
T half is given already, which is it given here? No, it's 4 right here. Can you see that? T half is 4. Same question.
So, okay, that's what I was trying to figure out. Okay, fine.
4. Now, Anas, tell me the answer, and Ayan, Shray, Neha in the chat.
Okay, so 1 second. So 142 into 1. Is that okay? Is it to the power of 12?
12 divided by 4.
So like Is it to the 1/2 to the power of 12 divided by 4?
Yes, exactly.
18.
18, that's the correct answer. Good. Now, Ayan, Shrey, Neha. Where's Neha? I can't hear you, Neha.
Sir, I answered in the chat.
I did too. Sir.
Right, yeah, I had to answer a call. Now, let's get back to the class. We have 18.
Who
We
gave
got
the
18.
answer first?
Say that again.
Who gave the answer first?
Who gave the answer first? It was Shrey this time. Shrey gave the answer first. Okay, I forgot to give the marking. Ayan, Shrey. So all of you have 1 point. Shrey has 2 points right now. Now, count rate 18. Okay, that's the activity of the sample. Now, is 18 the answer? Nope, it is not.
think.
No, look. So what we did first, the first thing was we did sample or activity was count rate or total count. A naught was total count. Let's say sample was total count minus background radiation. Let's say BR, background. Now the second step was find the activity. Then the third step is again to find the total count. Total count, we'll have to do this. Sample plus BR, we'll have to add that again. Is that clear? Now write the whole answer in your notebook, step by step. Background radiation.
Wait.
Now we know that the background radiation was how much? 16. So the total count is going to be 18 plus 16. Now at the beginning, the count rate was 160 at the beginning, fine. But after some time, the count rate decreased from 144 to 18 for the sample. Background radiation does not change. So at the end, to find the total count, we'll have to add these two back. And the answer is
Oh,
34.
all right.
Now do one thing, write the question as this. Write these in the question. So question is going to be this. Finding.
Wait, weren't we doing like reflection yesterday?
We were, that was revision, but we have to get back to the course timeline for you. We have to finish the syllabus and properly go to the chapter reflection. I can't do revision separately without, so you can take an extra class for that, but we're finishing chapters because this will also come in the exam, Anas.
Okay.
Right? These will come, guaranteed.
I
And these
think
require a lot of marks.
you're going to have the complete syllabus.
Yes, exactly. So find count rate when background is also involved or given. Now write this question and write the method, the steps right here. This is the question and the 3 steps are the answer. Write the whole thing, tell me when you're done, quick.
Can you give us a sample question instead?
I can give you the sample question, but I want this method to be in your notebook. And I want to see this method repeated in the next question I'm going to give you. Is that clear? So hurry up and write this down. The method.
Fine.
I want this replicated in the next one. We'll actually try another question like this. So we'll also try a different kind of question. Fine. Write the proper spellings, background radiation. Now, all of you, do you have any doubts in background radiation or where it comes from? Anas?
No, sir.
No.
Good. Neha, can you hear me? Welcome back to class.
Sir, can you hear me? Hello.
Yes, I can. Good.
Yeah.
Now
right.
on the screen, you have the question. This is the question right here. On the
Okay.
top, write that,
Yeah.
then write the answer here. That's the question, then answer. First step, sample is equal to total count minus background radiation. Second step, A is equal to A naught half raised to power this. And third step, total count is sample plus background radiation.
Okay, sir. I'll write that.
Write this. I want this method repeated in your answers. I don't want you to just, let's say, do your answers randomly. Follow a proper and let's say replicate a proper method every time. Do the same thing every time. That will help you create a habit. Another thing, this equation I don't think is given in your book. If it is, that's good. But in most books, it's not given. You usually get this equation in class 11. But I don't understand why you can't use this equation, because it makes everything simple. And it is also mentioned in your syllabus. So use the equation of activity. Fine. Don't do the first way we did it. Don't do it, let's say, into half, 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 or all of that. Don't do that. Follow a proper method. Now, Anas, how much have you written?
I'm writing the question right now. The second one, the B.
Which question?
B.
You don't have to write that. You just have to write this part. Look, this, and then the answer.
Okay. Okay.
Fine. Don't write that. I'm going to highlight it for you. Let's say. These 3 steps, guys.
Wait, do we have to write the uranium sample structure?
No, not at all.
Okay, we just write until 34.
Until 34, yes. This right here is sample E. Neha, how much have you written?
Sir, on the second step.
All right, almost. Done.
Okay, done. Fine. Ayan and Shrey, how much have you done? Ayan and Shrey, how much have you done?
Sir, I'm nearly done.
Almost done, sir.
I'm going to move on when the timer on the top right of the screen is going to reach 30 seconds.
I'm done writing already.
Done writing. Neha, how much?
Sir, the last word. 1 second. Just yeah.
Answer.
Yeah,
Fine,
done, sir.
we're moving on. The next type of question is Shreya, done?
Basically, yeah.
Yeah. Okay, good. Let's continue. Now, the next question is this one. Shreya, read the question.
The nuclear equation below shows the decay of plutonium Pu nucleus to a americium Am nucleus and a beta particle. Say the quantity that is represented by the letter Z in this equation.
Okay, what is represented by letter Z? This one
So
right
a
here.
beta particle is basically two, let me see, electrons, or
It's an electron. One electron.
one electron. Okay.
Wait, P means
And
beta,
alpha
right?
is two
Yes,
protons.
B means beta. Right now, we don't care about alpha, beta. They're just asking us, what does this letter mean? Now, I've told you, whenever we have this right here, let's say X, A, Z, whatever the X is, we don't care. A is always the nucleon number. The one above, a nucleon number. A is XZ, don't mean anything here. I'm just using them as symbols. Now, nucleon number is on top. This is called the atomic number, or number of protons. Fine. Atomic number or number of protons equal to number of protons.
Yep.
So in this, what are we going to write? In this answer, the answer is, please write this whole thing in your notebook. Okay, XZ, this is called the nuclide notation. Nuclide notation. Now you have to know this. Write this in your notebook. And the answer for this question, letter Z, is atomic number. Letter Z here means atomic number, as we know. If they asked us what is this 241 here, we would say the nuclear number, which is equals to proton plus neutron. Just a second. Proton plus neutron. Next, state the numerical value of Z. How do we find this answer? Now, you guys should know that alpha has this notation, 4, 2. Beta has this notation, 0, minus 1. And gamma has this notation, 0, 0. So alpha has how many, let's say, Neha, tell me, how many protons does an alpha particle have?
Two, sir, two.
2. Write this in your notebook as well. Decay particles. How do we know the number of protons? Because the Z, the number below, is always the number of protons, which is 2. And Ayan, tell me how many, let's say, okay, tell me how many nucleons does an alpha particle have? Anas, how many nucleons does an alpha particle have? It has 4. The one above is the nucleon number.
Sorry, an alpha particle.
Yes, alpha particle has 4. Beta particle has 0 nucleons, but it has minus 1 over here. Now let's solve this equation. Now Anas, Neha, Shreya, all of you, write both of these things here. This one and this one, if you haven't already.
Okay.
No, that's fine. I'll decide it.
We'll write that in a second. First, Anas, work with me on this question. How do we solve a question like this? They're asking us, what is the value of Z, right? Anas, where is Z?
It's the atomic number for Pu.
Pu, perfect. That's good answer. Plutonium. Now all we have to see is the beta particle numbers are not given, so we'll just write it first. Let's say it's going to be 0 minus 1. Now we need to know that 241, all the numbers above are equal. So 241 is 241 plus 0. Fine, that's okay. Z is equal to 95 minus 1. Therefore, what is Z? How much is Z?
94.
94. The answer is 94. Now write these things in your notebook. Decay particles and nuclide notation. Neha, read the next question.
The americium nucleus decays by the emission of an alpha. So that's alpha, right?
Alpha, yes.
An alpha particle into a neptunium nucleus. Complete the nuclear equation for this decay.
Fine. How do we solve a question like this? Again, first thing first is becoming an alpha particle. And it's also becoming neptunium plus alpha. This should be the equation. We're not getting anything else.
Yeah.
Now, I don't know what the,
Yeah.
the nucleon number for NP is or the atomic number for NP. Fine, but I do know that alpha is 4 and the atomic number is 2. So therefore, 241 is equals to, let's call this X and Y, is equals to X plus 4 and 96 is Y plus 2. So tell me, Neha, what is X and Y?
Sir,
Yes, speak louder.
so can you hear me? Hello. So hello.
Now we'll
The
find
answers in the chat.
answer in the chat. Anas, Ayan, work with me on this. What was the first step we did? We wrote the equation because I know that neptunium is going to be there and alpha particle has to be there, right? Now I know the atomic number and the nuclear number for alpha particle, but I don't know what neptunium is. You'll not be given a periodic table in this exam, by the way. So how do we solve it then? We'll write the nuclear number and atomic number for NP as X and Y. We can form two equations. We can find 241 is X plus 4 and 96, is it 96, 95?
95, sir.
is equals to X plus 2. Tell me the values for X and Y. Quick.
Sir, 93.
All right, so Y is going to be 93. All you have to do is decrease 95 with 2. This guy goes there, it becomes 95 minus 2 is equals to Y. And this guy goes there, you get
237.
24 minus 1. So 237. 241 minus 4 is equals to X. Fine. Now 93 and 237. Therefore, I'll just replace this X and Y here and write 237 and 93. Shreya, your answer is correct. Neha, do you understand how to solve a question like this?
Yeah, I did.
Good.
Right.
Let's move on.
Yeah.
Yes, tell me.
No.
Read this question, Neha.
Yeah.
Ayan, Anas, I want the answer from you in the chat, Neha, and I will work on this now. Start, Neha.
The half-life of this americium nuclide is 470 years. A sample of this nuclide contains 8 into 10 to the power 14 atoms. After some time, 6 into 10 to the power 14 americium atoms have decayed. Calculate the time required for this decay.
All right. Now we'll write our equation here. This is for the number of particles, right? Atoms. So we use N for this, not A, because it's not the count rate. So what was the
Yeah.
equation? N is equal to N naught half this part T half, or T divided by T half. Okay. Have they given the half-life?
No, they have not.
Read this line.
Oh wait, they have. So 470
This
years.
one.
Yeah.
So 470, we'll write that as T half. And
Yeah.
contains how many particles at the beginning?
It contains 8 into 10 to the power of 14.
That's our N0, N0. Now, after some time, this many have decayed. Okay, so this much has been gone. Fine, so this is decayed. So how do I find N? How much is remaining? This is how much I had in the beginning, and this much is gone. So what is left? Or N left is going to be 8, the original minus the decayed. Because the decayed particles are gone. So to find how much are remaining, we have two equations. We can find it in this way or also in this way. But we don't know the time. Is the time given?
No.
No, the time is not given. So we have to find the time they're asking us to find. So we can't use this equation. In this equation, we need to know the time as well. Fine. Now to find N, we'll just subtract how much is decayed from the total particles. Total particles were 8 into 10 to the power 14 minus 6 into 10 to the power 14. So how much is remaining, Neha?
1 second.
Well, 6 minus 2. 8 minus 6. How much?
2.
2 into 10 to the power 14.
Yeah.
Now that is the N left. So we can use this equation now to find T. N is 2 into 10 to the power 14. N naught was 8 into 10 to the power 14. Half raised to power T. I don't know what T is. But I know half-life, so which is 470. Now how do we find T?
So first you can take 8 into 10 to the power 14 there.
Okay. This will become
By
8 into 10 to the
yeah.
power 14. Half.
I'll do
Raised
that
to
first.
power 347. Then
1 second, I'm doing that thing once.
okay. Rest of you, have you gotten any answers?
Yeah, okay. So then what you do is you you multiply 2 to the numerator, if I'm not wrong.
Over here,
Oh no, wait. Sorry, I'm wrong.
it's not possible. I'll tell you how to do this one.
I
Okay.
got it.
Moving on, how to solve this question is we'll have to use something called logarithm. There are two ways. One way is to use the calculator or to use logs. Fine.
Yeah.
What are the ways? Now first simplify this. What is 2 into 10 to the power 14 divided by 8 into 10 to the power 14?
Into 10 to the power of 27.
No, this cancels out. Okay. And you're
That's it.
left
I
with,
did it in the calculator, so yeah, it showed me like that.
let's see. Okay. So 2 into 10 to the power 14, that cancels out. You're left with 1 over 4 is equals to half raised to power T by 270. Okay. Now, how do I find T? Well, to find T, let's make the base common. Okay, let's make these guys common. Can I write 1 over 4 as 1 over 2 squared?
Oh yeah.
Can I do that?
Yep.
Fine. And then half is equals half raised to power T 270. So what we're making is we're making these guys to make the power, to find the power, we need to make the base common. Now 2 is equals to T over 270. Therefore, what is T? 270 into
2. Yeah.
which is 540
5.
years. So the answer in this question is how much?
540.
Now the rest of you, any questions? How did we do this question?
Can you check
Ask me questions now. Anas, your answer is correct. Yes, good job. Well, no, it's not correct actually. No, it's not correct.
Wait, don't you do the half of T? So 470 divided into like half.
Well, yeah, actually, yeah, this is wrong by the way. This has to be half. Okay, and
It will be
no, this
470
has to be 2. Then this goes up. So 270 times 2.
How did you get 270?
How did I get 270? That's given in the, oh, it's not 270, it's 470.
Right, 470.
470. The half-life is given here, right? So 470, 470. And 470 times 2, tell me the answer. Share 470 times 2,
940.
940. That's your answer.
Hey, don't we do like 470 divided by 2? Because it says like over there in the formula, t divided by t 1/2. So half of 470.
Now we don't do t half. T half is equal to 470 on us. It's not t of divided by 2. Is that
Okay.
clear?
Yep.
So that's t half is like a symbol. It's not being multiplied, it's a symbol. Okay. Now we got the answer as 940. I want you to write the method. Now, Ayan, any questions? Share any questions? Ask me quick.
Not really, sir.
Time when,
Next question.
uh, let's say time when decayed. Let's say N0, half-life, and particles decayed are given. First step is you find the use the equation. So first step, use equation. Or let's say write equation. The equation is going to be what?
N equals
Ayan, tell me the
N0
equation.
half to the
Okay.
power t over t half.
Right, that's something you need to memorize very clearly. T by t half. Now, second thing is, second step, find n. We don't know what n is. To find t, we need to find n. To find n is equals to n naught minus decayed, the ones which are not present anymore. Third step is use equation. Finally, fourth, let's say solve equation. Solve equation by making base comment or calculator. Now write this down in your notebook. Tell me when you're done. Find t. Find t. Solve equation by, okay, yes. Now, Neha, you understand this question? Yes. Ayan,
Yeah, I did.
fine. Now we'll try something, a different kind of question now. There's these questions. I don't think you're getting anything else. All the questions are going to be of these two types. Perhaps if there's a third type, we'll go through it later. But these are the main two types. The questions are usually for 5 to 7 marks. So in the exam, that's a lot of marks. In 80 marks, you're getting about around 10 marks in radioactivity. So that's a big chunk of marks.
Mm-hmm.
What is the next class after this? Anas, check, tell me, what is the next class after this?
Next, what?
Next class,
Next class is ICT.
ICT. We're looking at decay, the deflection of decay particles in magnetic fields. Anas, tell me, how many decay particles do we have? How many types? Quick.
Alpha,
Yes.
beta,
Beta,
and
which looks like
it
and-
was like a white thing.
gamma.
Gamma.
Alpha, beta, gamma. Now, all of these are going to bend, or what is the meaning of deflection? Deflection basically means bending.
Bending.
Okay, bending. This is gamma. I also write the names here. So 0. This is 4, 2. This is 0 minus 1, 0, 0. Fine. Now we have these particles here. And now I'll also show you a magnetic field. So we have two kinds of magnetic fields. First, you have something like this going into the page. This is into page. What is it? Look, it looks like an arrow. Anas,
Yes.
this looks like an arrow, something like this.
Okay.
Now, what part of the arrow are you seeing in this case? The back of the arrow, right? Anas, what part of the arrow are you seeing over here? These cross. I want you to imagine it like the arrow is going away from you, like this.
Away.
So you're seeing the back of the arrow. This is the direction of field, let's say, direction of field. So the arrow is pointing away from you. So the field is into page or away from you.
Okay.
Direction of field. Okay, now let's see how the different particles behave. Let's throw in, firstly, we'll throw in, let's say, a beta particle, which is negative. Beta particles are negatively charged, yes? They have a negative charge, they're electrons. Now what we need to see is, since beta particles are going like this is negatively charged.
Okay.
So current direction, therefore current is opposite of negatively charged. Or let's say current is positive to negative. Yes, we know that current is positive to negative. Therefore, it is going opposite. Now, Anas, read this out loud. From here, from beta particle.
Okay. Beta is negatively charged. Therefore, current is positive to negative. Opposite to negative charge.
Look, if I have a circuit like this, okay, and this is the positive terminal, and this is the negative terminal. Where is the current? How is the current flowing? From which to where? From where to where? It is flowing from
Wait. Positive to negative.
positive to negative, like this. Fine. So it's going from positive to negative. But so but the electrons are going like this. Electrons are going opposite direction. Fine. So always current is opposite of to negative charge flow. Current is opposite to electrons. Fine. So if negative particle is going in this direction, the current is in the opposite direction. You see how negative is from negative to positive, like this. But current is positive to negative, so it's opposite of the flow of electrons. Current is opposite of flow of electrons. And that's what's happening. Okay. Now we need to realize one more thing. Okay. So if beta particle is going in this direction to right, beta is going in which direction, Anas? Right now.
Beta is going into the page.
Not into the page. No, that's the magnetic field.
Oh,
The beta particles are going to the right.
to the right. Okay.
Right. Therefore, what is the direction of the current? Current will be to where?
Current
To right,
going, yeah,
to
to the left.
left. Good job. So you're intelligent. Right, you're one of my most intelligent students. So please just work hard and you'll get very good marks, inshallah. Look at this. So to left, fine. Now we have field and current. Can I find motion? How do I find motion, Anna? With the left hand rule. So use the left hand rule and tell me the motion. Direction of motion.
Okay. So I'm supposed to find the motion.
Yes, you have the current, you have the field. You have
Okay,
to
so-
find the motion.
Current is to be this into so upwards.
Upwards. Perfect, upwards, okay. Upwards, upwards. Yeah, you know that. So that's the correct answer. Anas, very good. Good job. I was going to show you the diagram to help you, but you found the answer on your own. So that's very good. Now this is the diagram. You used it, and we realized the motion is upwards. How do we know that? Because I'll just make a diagram. Let's say this is the field. Let's say the field is inside. That's the field. And the current is going in this direction to left. Current is going. No, Anas, try again. Tell me what is the direction of the motion. Current is left.
Current is left, and then field is into the page. So wait, out of the page.
So it's away from you, Anas. Away from you.
Okay, how?
Look, if I rotate it, how? Okay. Look, if I can show you, let's make a hand. So the field is going like this, right? The field is going away. Let's say away from you. And then your current is going to the left. Okay. Then the thumb will be downwards. You'll have to rotate your hand. So this is your index finger. Let's say this is your. Okay. The field is going away from you. Okay. And your thumb, the current is right. Now, what I want you to do is, what I want you to do is basically put your hand, make your thumb, let's say, make your index finger point away from you. Tell me when you're done.
Wait, so index finger away from me.
Yes.
Okay, index finger is away from me, and then current is to the left.
And your middle finger will be to the left. Index finger away, middle finger to the left. What is the direction of your thumb now?
Okay, index finger away from me, this to the left, and it's downwards.
Downwards. Is that clear? Do you understand how now?
Yep. So do we
So
just
this is going to
rotate our
be-
hand?
Rotate your hand. Yes, you just rotate your hand. You have to make sure the current and your index finger, the field and index finger are in the same direction. Current is left, so you'll rotate your hand. You'll get the thumb going downwards. That's the motion. So this is down. Any doubts? So the motion is downwards. Fine. Therefore, this particle, this alpha particle, this beta particle is going to bend like this. How will it bend? It will go like this. Any questions?
No.
Now that's the case one. Okay, which is beta and field away, field into page. We'll try one more of this. Let's try, let's say, okay, what if we try alpha particles now? Field into page. Now, by the way, Anas, your ICT exam has been finished or is it remaining?
What?
Your ICT exam, is it done or remaining?
It's done. We're done with our exams.
Fine. So we'll just finish this and then we'll finish ICT after this. Okay.
Yeah.
Now,
that's fine.
case one is field into page. Now, fine. Field into page is basically into the page or away from you. Now, next thing is we did beta particles. What about alpha particles? Let's use some other color for alpha. Let's use red to say alpha. 4-2. What will happen to alpha particles if they go into the page? How will they react? So now, Anas, what is the charge of alpha particles?
Wait. What is
What is
it?
the charge of alpha particles?
Okay, so if it's positively charged, then therefore
And current is in which direction?
the current will like turn into negative to positive.
It's always positive. No, it will not switch. We only
Oh.
switch for negative particles. For positive particles is the same. So current is now
Positive.
right.
So wait, to the right?
Yeah, tell me. Yes, to right.
Isn't it?
We only isn't it?
Isn't it to the left because beta was negatively charged and it was to the right. So for alpha, it would
No,
be.
yeah. Beta was to the right. No, okay, look. Beta is going to the right, but current for beta was to the left, right? For beta, the current was where? The beta was going to right, but the current became left, the opposite. Okay. So for beta particle, we flip the direction. But for alpha particles, we're not going to flip it. Is that clear? Think about it and tell me.
Okay.
So for alpha,
Well,
now first tell me where is the alpha particle going?
to the right.
To the right. It's also going to the right. But okay, but the current direction is not going to be opposite to it because it's not negative. We only flip current direction when it is opposite. Both of these are going to right. Fine. Okay, since they're going to right and alpha is positive, current will also be to the right, same direction as positive. So we'll first write the field. What is the field, Anas, in the question? It is into page, right? Why is it into page? Because the arrows are going away from you. Anas, you muted. Tell me, what is the direction of the field in the question?
Of the field. So for alpha, right?
No, a field is not changing. Field is
Okay.
based on these arrows, these cross
So it's still
into
downwards.
page. Downwards, not downwards. It is away from you or into the page. Is that clear?
Yep.
Into page, still into page. Downward would be like this, Anas. This is downwards. But this cross is like the arrow going away from you. This is down, this is right, this is up, left. That's fine. We show arrows down, up, right. But away is using an across. Away means across means away. Across means into page, which is the same as away. And dot means out of page. What does the dot mean, Anas?
So like what are the x's, like so many x's for?
Say that again.
What are the x for, like the x?
X is like the back of the arrow. You see this arrow right here. Now, if the arrow, if you're only able to see the back of this arrow, that means the field is going into the page. Is
So
that
is
clear?
it always into the page?
Always into the page. X always means into page. Is that clear?
Okay.
And dot means out of page. Is that clear? Dot means out of page.
All right.
Now let's see. Next thing, we have to find the current direction. What is the current for alpha? Alpha is going to right. and it is positively charged. So what is the current direction?
Okay, so
Yes.
wait, did you ask a question?
Yes, I asked a question. The question is, alpha particle is going to right. Then what will the current direction be?
It will always be the same. So into the page.
That's the field. Field is into page, done. What about the current?
Current is so field is into the page and then
Now,
that's
Anas, I'll tell you what the current is. For alpha particle, current is the same as the direction of alpha. Fine?
okay.
It is same. It is positive to negative. Positive to negative. And since alpha is positive, so wherever the positive charge is going, that's my current direction. Okay? So for alpha, it is positive. For alpha, it is, for alpha, same as, let's say, same as alpha direction.
Okay.
But for beta, what was the case? It was opposite, right? For beta, it was opposite direction. Now let's look at third case, the motion. Now use the left hand rule, tell me the motion.
Left hand to then motion. Okay.
You know that the field is into page, current is right. What is the motion?
Current is it upwards?
Upwards. Good job. Left hand rule. So
Into page
Yes.
means into the page means away from me, right?
yes. So upwards. So the alpha particle goes opposite direction to electrons or the beta particles. It will go slowly, not much. It will not bend too much. It will bend a little bit. Why is that, Anas? Why do you think it is like that? Because alpha particle is heavy. Fine.
Okay.
So bends less than alpha, less than beta.
So we have to
Less
also
than
draw a
beta.
line like that.
Yes, bends less than beta because heavier. Any questions?
No.
Now
Wait,
let's
can you
look at,
drawing the line part again?
yes. Can you see it?
Yeah.
Any questions?
No, like can you explain it again? Like how do you draw the-
Explain. Okay, I'll explain it. Let's explain it one more time. The field was into page. Okay. Next thing is alpha is going to the right. So okay, alpha is positively charged. So the current must be same as the direction of positive charge, or same as the direction of alpha. Okay. So
okay, so it's just going to go to the last X, but just bending a little bit because of the
yeah,
weight.
bending it not to the last X. It doesn't matter where it's going. You can draw it any way you want, but it should be not as much as beta.
Okay.
Less than beta, like this. Direction does not matter which X is it passing through. We just have to show it's going up. Okay.
Is there one for gamma too?
Yes, we're doing that one now. We'll make gamma, and for gamma it's very easy. Gamma does not bend at all. Gamma goes straight. Fine. Gamma goes straight into the through it. It does not bend at all. Any questions?
No. Okay, yeah.
Why
that's-
does it not bend? Why does gamma not bend?
There is no weight on gamma,
There is no charge on gamma.
no charge on gamma.
So there cannot be any current because if you don't have charge. So that is all you need to know. Now I'll summarize this. Case 1. Write this in your notebook. Field, let's say, write it in your notebook. Direction of particle, then field into page, which also means X, right? Which means X. So first we'll start with alpha. Alpha is up upwards, beta is downwards. 3. Now, Anas, you have to understand how this is happening as well. You can't just memorize, but please first write this down. Gamma is no change, no deflection. Now, case 2, second case, when the field is not, it's out of phase. The direction switches. This becomes downwards, beta becomes upwards. Write both of these in your notebook.
Yeah,
Tell me
so
when you're done.
I'm on case 1 beta part.
Okay. This is very important. This usually comes in MCQ, always.
Not even almost.
Done.
Yeah, I'm on the case 2 beta. Okay. Last sentence. Okay, done.
Done. Fine. Now, I think let's just do one question on this. Fine. Let's do a question on this.
Sure.
I'll have to open the MCQ book, and the topic is radioactivity. There are 256 questions on radioactivity in the book.
Oh, nice.
Let's see. Let me find the question.
Wait, do you guys also like give like the books instead of the PDFs?
Just a second. Now look at this one. Now read the question, Anas. Skill check.
An A particle enters a uniform magnetic field directed out of the page. In which direction is the A particle deflected by the field?
Now look
So-
over here. Yeah, stop. Now, can you see these arrow dots here? Instead of cross, there's a dot. It's like if you look at an arrow, and if the arrow was coming towards, you would see only this nook of that, right? That chord point of that, instead of the cross, the back. So we're seeing it's coming towards you, fine, and alpha is going up. So we have to use the left hand rule here.
Okay.
Left hand rule. So we need 3 things for left hand rule. We need the magnetic field.
Wait,
What else do we need?
the same for left hand rule? Is it the same?
Say that again.
We're still going to use the left hand rule?
Yes, always left hand rule in
Okay.
this, because there's no EMF being induced. There is a particle with charge. Now field and current, and we need to find the motion.
Okay, so the field for alpha is
What is the direction of the field?
to the left. No, to the
No,
right.
field is given in the question. Tell me, where is the field going?
Nearby the current is,
Directed
out of the page.
out of page or towards you? Same thing. We'll write out of page here. Out of page,
So it's towards us, right?
towards us. The arrow is coming towards you. This arrow is coming
And then
towards you.
A particle,
Alpha particle.
alpha particle,
So current is going to be
current is going to be same. Okay, same.
same as alpha.
P.
Now where is alpha going?
Into the page.
That's going up,
Oh,
right? Into the page is always going to be like a cross, right? Yes, the alpha is not going into base, it's going up. We'll write upwards. Now find motion with the left hand rule.
So current is up, and then the field out of the page.
Out of the page. So it's going to be towards you.
Left.
The field is out of the page.
Yeah.
Okay.
So the motion is towards us. So out of the page, B is the answer.
So where is the motion?
So wait, one second, let me check again. So current is upwards, and then that's out of the page, and then yep, to the out of the page. No, no, no,
Nope,
no, no,
that's
to the
no.
right, to the right, to the right. Wait,
the
no,
right,
to
exactly.
the left, to the left. Yep,
the
to
left?
the yeah, to the left.
Let's see. And let's try one more time.
Wait, so the field is out of the page, so towards me, and then the current is upwards. So if it was like this, then we rotate it, and then yep, it's to the left.
Okay, do one thing. Anas, point the current up. So your middle finger upwards.
Yes.
Okay. And then point your index finger towards you.
Yep.
Where is your thumb pointing?
It's to the left.
Are you sure?
Yes.
Okay, okay. Turn on your camera. Show it to me.
Okay, one second.
Okay. Now, okay. The current is okay. Okay. Look. First, make your hand like this. Now keep your camera on so I can see what you're doing. And this is like it. This is how it is. I need your fingers to be like. Are your fingers like this?
Yep.
Fine. And now put the turn on your camera and put your index finger, first finger towards you.
Okay. Towards me.
Turn on the camera.
Once again. Like this.
Towards you, right? Okay, just do it properly. And keep the camera on.
It's like this.
Like this. Now towards you. Now all you have to do is you have to rotate. Now keep it like that and make the third finger, middle finger, point up.
So up and then towards me.
Take your time.
Yeah, like that. So to the right.
To the right. Make sense?
Yep.
It's going to be to the right. Now, I'll show you a trick after we're done with all of this. There's a trick. You don't have to use a hand for this. Fine? But not right now. You have to be happy with your hand. Using it comfortable, then I'll tell you how to find it in another way. Afterwards, a motion. There's a thing you can do with your scale. But that's afterwards. Now motion says to the right. Fine. So the answer is, what is the answer of the question, Anas?
D.
D. That's how you do this one. Now you'll get more questions like this. All you have to do is know that if you have alpha, the direction is same. But if you had beta, then current will be opposite to the direction of beta. That's it. Then use left hand rule and get the answer. That's all for now. Any questions?
No.
Recap, what did we learn in this class? Quick.
We learned how to wait. We learned about the X thing where the arrow was going into the page, and then we have to find the alpha particle, beta particle, and gamma particle. And then we did
Class deflection.
half-life.
Half-life. half-life questions. How to find the time and how to find the
Yes.
activity and the number of particles.
Then we use the formula n equals n naught into 1/2 to the power of t by t half.
Yeah, perfect. That's very good. Very good. Good job. Alhamdulillah. Right. That's all for now. Just a second.